Atomic mass units and moles are units of measurement in chemistry which allow us to easily work with very small and very large numbers. For example, the mass of a hydrogen atom is 1.6735 times 10 raised to the negative 24th grams. It is inconvenient to work with numbers like this for such small objects, and so chemists use the atomic mass scale instead. One atomic mass unit is equal to 1.66054 times 10 raised to the negative 24 grams. So in order to find the mass of a hydrogen atom in atomic mass units, we multiply the mass by the conversion factor, consisting of one atomic mass unit divided by 1.66054 times 10 raised to the negative 24 grams. The grams cancel out, and we end up finding that one hydrogen atom has a mass of 1.0078 atomic mass units, or AMU. A hydrogen atom consists of a proton and an electron. Electrons have a mass that is negligibly small compared to a proton. As a result, we generally round the mass of an electron down to 0 and just estimate that the mass of a hydrogen atom is equal to the mass of one proton inside the atom's nucleus. So one proton has a mass of about 1 AMU. For atoms containing neutrons, the mass of a neutron is almost identical to the mass of a proton, and so we say that a neutron also has a mass of about 1 AMU. So we can estimate the mass of a given atom by counting the total number of protons and neutrons in the atom's nucleus, which gives us the mass in AMU. For example, let's take an atom of carbon-12. Carbon-12 has a mass number of 12, which tells us that carbon has a total of 12 protons and neutrons combined. Since each proton and neutron has a mass of about 1 AMU, we would estimate the mass of the carbon-12 atom to be 12 AMU. Actually, the atomic mass unit is currently defined as assigning a mass of exactly 12 AMU to a carbon-12 atom. But many elements exist in different isotopes, which have the same number of protons, but different numbers of neutrons. As a result, these isotopes have different total atomic masses. For this reason, when we look up the atomic mass of a given element, we are actually looking up its atomic mass averaged over all of its isotopes found in nature. For example, in the universe, the majority of hydrogen atoms have a nucleus consisting of just a single proton and no neutrons, corresponding to a mass of about 1 AMU. But there are also cases of hydrogen isotopes that have 1 or even 2 neutrons in the nucleus. These cases are extremely rare in nature, though, and so they contribute negligibly to the average atomic mass for hydrogen. Let's do another example. 98.93% of all of the carbon atoms in the universe are carbon-12, and only about 1.07% of all the atoms in the universe are carbon-13. Since carbon-13 has one more neutron than carbon-12, we would expect the mass of carbon-13 to be about 13 AMU. Carbon-14 isotopes also exist, but in negligibly small quantities. To find the average atomic mass for carbon, we convert the percent abundances into decimals. So that's 0.9893 for carbon-12 and 0.0107 for carbon-13. We then multiply the mass of each isotope by its respective mass, and then add these numbers. So that would be 0.9893 times 12 AMU plus 0.0107 times 13.00335 AMU. This results in a weighted average value of the atomic mass of carbon, and it equals 12.01. This weighted average is referred to as the average atomic mass, or the atomic weight of carbon. Note that if all of the carbon in the universe was carbon-12, then the atomic weight of carbon would be exactly 12 AMU. But because there is a tiny fraction of carbon-13 in the universe, and this fraction has greater mass, there is an extra 0.01 in the atomic weight. If carbon-13 were even more abundant, then the atomic weight would be even closer to 13 AMU. The atomic weight is shown with the element symbols on most periodic tables. Since the atomic weight is on the periodic table, you can use it to find the masses of molecules. For example, H2O consists of 2 hydrogen atoms, which each have a mass of 1 AMU according to the periodic table. One oxygen atom has a mass of about 16 AMU. So 1 times 16 plus 2 times 1 gives a total mass of 18 AMU for one water molecule. We can call this the molecular mass or the molecular weight. H2O is a covalently bonded compound, so we can call it a molecule. Therefore, we can say that 18 AMU is the molecular mass of water, or equivalently, the mass of one molecule of water. But when there's an ionic compound like sodium chloride, NaCl, we can't use the word molecule, so we call the weight in AMU the formula weight of NaCl. But the calculation is done the exact same way. We look up sodium on the periodic table, and it has an average atomic mass of 22.99 AMU. We then look up chlorine, which has an average atomic mass of 35.45 AMU. We add these together and find that sodium chloride has a formula weight of 58.44 AMU. Now, moles are another important concept. A mole is basically a shorthand unit for a very large number. Just as we say a dozen eggs to refer to 12 eggs, we can say 1 mole of atoms to refer to 6.02 times 10 raised to the 23rd atoms. This very large number is named Avogadro's number after the 19th century scientist Avogadro. So 1 mole of carbon-12 atoms is equal to 6.02 times 10 to the 23rd carbon-12 atoms. Like any counting unit, Avogadro's number can be used with any object. So 1 mole of water molecules is equal to 6.02 times 10 to the 23rd water molecules. 1 mole of sodium ions is equal to 6.02 times 10 to the 23rd sodium ions. And it turns out that the value of 1 mole is directly related to the definition of 1 atomic mass unit. We've already seen that 1 molecule of water has a mass of about 18.0 AMU. If we have 6.02 times 10 to the 23rd molecules of water, which is 1 mole, we can find the total mass of 1 mole of water molecules by multiplying these two numbers. We multiply 18 atomic mass units times 6.02 times 10 raised to the 23rd. Next, we recall that each atomic mass unit is equal to 1.66054 times 10 raised to the negative 24 grams. Multiplying all these numbers together, we are left with the result that the mass of 1 mole of water is 18.0 grams. This quantity is also known as the molar mass of water. Now, the reason the calculation results in a nice whole number is that 1 atomic mass unit, 1.66054 times 10 raised to the negative 24 grams, is actually defined as 1 divided by Avogadro's number in grams. It is important to keep track of terminology here. A single molecule of water has a mass of around 18 AMU. An entire mole of water molecules will have a mass of around 18 grams. So we use atomic mass units when dealing with very small numbers, like the mass of a single water molecule, and we use moles when dealing with very large numbers, like the number of molecules in 18 grams of water. If you filled a graduated cylinder with 18 milliliters of water, you would have roughly 18 grams of water, because the density of water is 1.0 gram per milliliter. So 1 mole of water molecules can fit in a small graduated cylinder. 1 mole of other substances can take up substantially different volumes depending on their density. For example, oxygen gas is less dense than liquid water, so 1 mole of oxygen gas will take up more space than 1 mole of water molecules and can even fill a balloon. To see how to use Avogadro's number in a calculation, let's say that we have 0.00833 moles of sucrose molecules. Because we know that 1 mole consists of 6.02 times 10 to the 23rd molecules, we can use this quantity to convert any number in moles to a number of molecules. We multiply the 0.00833 moles of sucrose by Avogadro's number, 6.02 times 10 to the 23rd molecules per mole. The units of moles cancel out of this calculation, and we find that we have around 5.01 times 10 to the 21st molecules. All right, as a quick recap, 2 related units of measurement in chemistry are atomic mass units and moles. Atomic mass units are used to measure the masses of small objects like a single atom or a single molecule. Moles are a counting unit used to measure large numbers of objects like atoms or molecules. The relationship between AMU and moles allows us to relate masses that we can measure in the lab to the actual number of atoms or molecules in a substance.